thanking Micaela, Mariana, and Irene for putting together this very nice workshop, and thanks for the invitation to give a review talk about Swampland here. It's just such a pity that we cannot be there in Banff in person. And one of the things I was looking forward to doing in Banff is hikes around the snowy mountains that we were seeing in Linda's background. So since we cannot do a hike around Banff, let's take a hike through the Swampland instead. Okay, so I'm gonna give you during the next an hour and a half some quick review. We're gonna get like a very quick view of what is the Swampland and what kind of research is done in the Swampland program. So I'll start with explaining what the Swampland is from first principles, because this meeting is to bring together two different communities, and I'll introduce the Swampland for people coming from more generalized geometry or even mathematical backgrounds, which are not necessarily that familiar with what that is. And then I'll cover some recent results. Out of the many things people are working in the Swampland arena, I'll focus on some recent results in which we will emphasize the connection to various forms of geometry. So in Swampland, you use all sorts of mathematical techniques coming from algebraic topology, differential geometry, and so on and so forth. And I'm going to focus on the ones that are related to geometry. And just like in any hike, it's not usually a good idea to try to rush to finish it to the end. You need to take it at a slow, steady, nice pace to stop and observe the scenery. And because I want to do this, I want to do the same in this hike. Throughout the talk, I will be throwing in some questions that will hopefully lead to discussion. So the idea here is not that this is not just going to be like a one review talk that I go through everything to the end, but at some point we'll stop and hopefully there'll be some discussion with contributions from some of the swamp rangers that we might encounter in our hike along the swamp. Okay, good. So that's the poetic way to explain it, perhaps. But in case it wasn't clear, this is an interactive review talk. So just interrupt me at any point with any question, any comment, and I'm just gonna stop myself with questions of my own at some points. Okay. Good. So let's get going. What is the swamp? Let's take one step back and say that we are interested not just in the Swampland, but perhaps in quantum gravity in general. Well, and we're interested in particular in understanding what are the low energy predictions that one can get from a quantum theory of gravity. If one is interested in these kind of questions, the first hurdle one encounters is that when one writes down the Lagrangian, the Einstein-Hilbert Lagrangian for gravity, there appears an energy scale with an inverse power. So there's like a dimensionful coupling, and this scale, which is just the Planck scale, is huge. And that basically means that gravity is very weak, and it's very difficult to access it directly in experiments like the ones that we can do at colliders, right? So what can one do if one wants to understand what is the nature of quantum gravity or regimes where gravitational effects are strong, but one cannot access them directly experimentally? Well, one could give up, work on something else. A perhaps more interesting approach is to still work in quantum gravity, but focus on theoretical problems, on the kind of problems that one can still understand without just from theoretical means. And there's a bunch of problems like that which are very interesting in quantum gravity, like problems related to black hole evaporation. There are some arenas such as cosmology where the very high energy densities naturally involved in these processes can perhaps counter to some extent this hierarchy. But in general, it seems very, very difficult to imagine that there's any consequences of quantum gravity at very low energies, in the deep IR, in the energy scales that one can prove with LHC or other kinds of experiments, particle physics energy scales. Well, the basic idea of the Swampland is the observation that this very natural principle, this very natural thought seems to be wrong. So there's ample evidence coming from string theory that there are constraints, there are universal constraints on the IR coming from quantum gravity effects. And the way this comes about is that when I wrote the Lagrangian that I wrote down for pure gravity, I was too quick. Gravity is just not sitting by itself. It's also coupled to matter. It's coupled to, so that means that on top of the gravitational Lagrangian that I wrote down, there is also a Lagrangian describing a quantum field theory, an effective field theory part, which is coupled to gravity via this square root of minus g term. And this Lagrangian here is describing, in our world would be something like the standard model, is describing the, it's just the Lagrangian for an ordinary quantum field theory. And so in principle, when one writes down a Lagrangian like this, it would seem that one can just, write down whatever quantum field theory Lagrangian one wants here and just couple it to gravity in this way. So if one draws this blue blob, which could be, which one would imagine is the space of all quantum field theories, one would imagine that any point in the blue blob can be consistently coupled to gravity. But there's evidence that this is not the case. Okay, so the actual picture that is more correct is that this blue blob of all quantum field theories can be separated, can be neatly separated in two regions. There's one region, there's some blobs that can actually be coupled to quantum gravity, and most of them, the vast majority of them, are actually inconsistent. So the blobs that live in the green region that can arise as the long-range effective field theory of quantum gravity are said to be in the landscape, and the rest are said to be in the swampland. So that's the basic idea of the swampland, that not everything goes when you couple to gravity, and more importantly, that we can say concrete things about which stuff is allowed and which stuff isn't. So we can make universal predictions, we can describe universal features that the theories that can be consistently coupled to gravity must have. So if an idea like the swampland is true, it's really big news. It means that one can put constraints on the matter sector that wouldn't be apparent from any effective theory point of view. Can possibly say interesting things about inflation and hopefully address some of the big problems that are out there, like explaining why some of the parameters in the standard model have the hierarchies that we observe they have. So if it's true, it's extremely exciting, but what is the evidence for any of this? Why should you believe that any of these things are true? Well, I'm gonna explain a little bit what are the two main lines of evidence that you get for swampland constraints. So we believe the swampland constraints are true because often they are supported by general arguments coming from black hole physics. These are arguments that, even though they are not complete proofs, they involve universal ingredients that are present in any theory of gravity, like the physics of black hole evaporation. And so they're arguments that apply in any quantum theory of gravity. Those arguments makes us think that one or another statement is actually true. And then we actually check these statements against empirical evidence coming from string theory. So string theory provides a vast landscape of solutions, and one can check any given swampland constraint against string theory compactifications. And if one finds that something is true in a myriad of string compactifications and is also supported by black hole arguments, then the idea is that this statement is probably true. Any questions so far? Okay. One could take this one step further and ask if any of this can be proven. And the answer is that sometimes you can prove these things, sometimes in restricted contexts that don't cover all the examples. And the reason is we don't have a framework as of now to prove things in general in quantum gravity. And so because we cannot strictly prove these things outside of restricted contexts, which are sometimes very wide, but which are never as completely general, we like to organize our knowledge about what things are in the landscape of which things are in the swampland in terms of conjectures. So these conjectures are statements with different degrees of validity. And importantly, they are very much interrelated among them. So I just drew 4 conjectures here, which are the ones I'm going to be talking about within this review. They're perhaps the biggest ones in the Swampland program, and they are tied very strongly to important particle physics problems. Although I'm not gonna discuss the phenomenological implications in this talk. So people working on the Swampland, on one hand, we try to prove these conjectures in as general a setup as possible. When we cannot prove them, we check them. And also our job is, when we find a principle that has worked successfully in a bunch of examples, we try to extend it or to apply to new setups to propose new statements of interest that might be true. So that's the big picture of what the Swampland is. And there's many reviews about it. The most recent one is I think it's still true. Is this one by Viz, Calderon, Mitfendesky, and Valenzuela. And so I recommend that you have a look at it. In any case. Okay, so I'm gonna talk a little bit about all these conjectures and explaining first the conjecture, the motivation, and then trying to connect with some recent developments in the Swampland literature also related to geometry. Okay. Maybe it's a good point to stop if there's any question about the program, about the Swampland program in general, because I'm going to focus conjecture by conjecture from now on. Okay, so no global symmetries. No global symmetries is perhaps the oldest, best established Swampland conjecture. It's kind of like the flagship of the Swampland. It's really old. So it can be found, stated explicitly in a paper of Banks and Dixon from '88, but some statements along these lines can be traced all the way back to Wheeler. And so to understand what the statement that there's no global symmetries in quantum gravity mean, we first need to understand what is a symmetry, or equivalently a conserved charge. So it's a conserved charge is any quantity which is conserved in any dynamical process. So for instance, here we have a famous process, which is a beta decay. So a neutron decays into proton, an electron, and an antineutrino. And in this process, in the standard model, there's two conserved charges, but the two of them are of very different nature. On one hand, there's electric charge. The neutron is a neutral particle, and so the endpoints also have the total charge, electric charge must be 0. And there's a different charge which is conserved in this process, which is B minus L, baryon number minus lepton number, which is conserved in standard model interactions. So B minus L of 1 here is conserved because B minus L on the right hand side is also 1. Proton has +1, and these two guys have either +1 and -1. Okay, but there's a very important difference between these two charges. On one hand, the electric charge is what we call a gauge charge. It's a charge associated to a long-range gauge symmetry. What that means in practice is that the charge can be measured from far away. You don't need to go into the details of the collision to know that there was an electric charge or that the electric charge was 0 to begin with, because you can measure it far away using Gauss's law. You just compute the total electric flux as infinity, and from that you can compute exactly what the electric charge of the configuration inside is. So that's what a gauge symmetry is. And by contraposition, a global symmetry is a conserved charge like this, which cannot be measured in this way. It's a charge which is not associated with any long-range way of measuring. Okay, so for instance, in the standard model, again, we can measure electric charge very easily, but there is no way for us to measure the B minus L of a configuration without actually going in there and measuring how many protons, how many neutrons are in the configuration. So that's a global symmetry. And the conjecture that there's no global symmetries is that this kind of thing, which makes complete sense in quantum field theory, is actually in the Swampland once we couple to gravity. So you don't have global symmetries. So let me first explain why we believe there's no global symmetries, and then let me work out a little bit the interesting consequences, which is in the end the most fun part of it, and where we connect with more modern literature. So why do we believe there's no global symmetries? Well, there's a heuristic argument. Which involves imagining that we had some global symmetry in quantum gravity. So imagine you have a theory where the number of blue particles is conserved. So you start if you start with in such a theory with a configuration with a large number of blue particles, and the configuration collapses, and you make the configuration collapse into a black hole, then if the global symmetry was conserved, the particle number of B0 must be carried by this black hole as well. And the black hole, then, what does a black hole do? Hawking taught us that a thing that happens universally in quantum gravity is that the black hole evaporates, a Schwarzschild black hole evaporates. This black hole would evaporate until it gets some small size. And one can compute that the radiation that is leaving the black hole doesn't carry any global charge. It carries the same amount of particles and antiparticles. And so in the end, it would evaporate to some small object, which would carry a large amount of this charge. Now, if you follow this argument with any value of this initial charge B0, this initial charge could have been 1, 2, 3, 4. So you end up concluding, although there's several subtleties in here, that you will have infinitely many number of objects like this, stable objects protected by this charge, which one would call black hole remnants. They would be basically the generating mass. And so they would contribute to loops and ruin any effective theory computation. In quantum mechanics, every state in the theory contributes via loops to any other process, and very massive states are usually suppressed. But if there is literally infinitely many of them, their contributions to loops would ruin any calculation. So that this whole paradox you get into can be solved pretty easily if one starts by denying the first assumption, which is that there was an exactly conserved charge that you can measure from far away. Okay. So that is the heuristic argument I described. But this heuristic argument is actually supported by lots of evidence. This Swampland conjecture is by far, I think, the best established one. So on top of the arguments about absence of remnants that we talked about, which are kind of heuristic but very general, you can actually prove that there's no global symmetries in perturbative string theory. And essentially the same proof carries over to holography. So in the context of quantum gravity in area spaces, via the area safety correspondence, the absence of continuous global symmetries is actually equivalent to Noether's theorem in the dual CFT. So if you believe Noether's theorem, which is a pure quantum field theory statement, you get the similar statement you get the statement that there's no global symmetries in the dual field theory. There's recent proofs of the absence of global symmetries using all this new story about entanglement on islands. So when wants to reconstruct the Page curve of an evaporating black hole in a theory with global charges, the computation actually leads to some kind of paradox, providing support for this for this conjecture again. And finally, it is always true in every string theory example, and it sometimes is true via convoluted ways. It's gotten to the point that I don't think anybody in this community would think to have found the global symmetry in quantum gravity. If it seems you found a global symmetry in a string compactification, you look for the instant that it's actually breaking the symmetry. Okay, so this is the evidence for absence of no global symmetries. Any questions about this or about the conjecture itself? Okay, so now let's talk about consequences, which is the real fun part. The absence of global symmetries actually has real world consequences. As I was telling you before, if you look at the standard model, B minus L is a global symmetry. And therefore, no global symmetry it's telling you that actually cannot be the case in the full quantum gravity. The fact that it seems a global symmetry must be some sort of artifact of the low energy effective theory that the standard model is. So what are the possibilities? There's basically two possibilities. Either the B minus L is actually a gauge symmetry, which means that it's coupled to some long-range gauge force, some fifth force, which we haven't measured, and its coupling will have to be very, very small to account for the fact that we haven't observed it yet. Or the other possibility is that B minus L is actually not a global symmetry; it's actually broken. This is often what happens in gut scenarios. And it leads to predictions, because if this symmetry is broken, some processes that are forbidden in the standard model actually become possible. So, for instance, one could have double beta decay or proton decay. So, Swampland principles are telling you that one of the two must be true. Okay. So that's an interesting, really down-to-earth consequence of no global symmetries. But if you think about it, it's not a very strong. Is not a very strong constraint, because I told you it's either gauged or broken. If it's gauged, the conjecture doesn't tell me how weak the coupling is. If the coupling is very, very small, I might as well say it's a global symmetry, because there wouldn't be any practical way of distinguishing them. And if it's broken, it doesn't tell me at which energy scale it's broken. If it's broken at such a high energy scale that the symmetry violating processes are extremely rare, I might as well say that they're global. So even though it's a very interesting conjecture with consequences for the real world, it doesn't seem to have a lot of teeth by itself. Okay. So now we get to some of the more recent developments along this conjecture, which is that I would say that certainly in the past 3 or 4 years, it's true, it has been realized that if you combine this theory with perhaps supersymmetry and anomalies and considerations based on supersymmetry and anomalies, in particular in higher dimensional theories, it actually gets a lot of teeth. It becomes a very strong statement. Okay, which I'm going to describe now. Are there any questions now? I think there's some in the chat. Okay. So yes, just mute yourself and ask at any point, please. Okay, so how can this conjecture become so strong? Well, so this is based on work by several groups over the past 2 or 3 years, and basically using supersymmetry, things are it's the usual story. Supersymmetry constrains things so much, and combined with this conjecture, it can be so constraining sometimes that you can actually use the Swampland to make very precise predictions about the low energy effective field theory that actually match constructions in string theory. Okay, and in some cases, if you're in high enough dimension and with enough supersymmetry, this match is perfect, meaning Swampland principles are enough to recover everything that you get from string theory compactifications. This idea goes under the name of the string Lampos principle, or in some other parts of the literature, it's called the string universality. The idea of the string Lampos principle is that one could complain that by looking at string theory compactifications, one is suffering from some sort of Lampos effect, where the kind of theories that one is looking at are not representative of the full class of solutions that you might have in quantum gravity. And the string Lampos principle actually tells you that the Lampos actually covers the whole street. It's really a good Lampos, and it's true for these higher dimensional compactifications. Okay, it's gotten to the point where the Swampland task is essentially complete at the level of massless fields in 8 dimensions and 9 dimensions. So let me explain to you how that happens. So if one focuses on theories, on supersymmetric theories in 7, 8, and 9 dimensions, life is very simple, because there's just 2 kinds of multiplets, of supersymmetry multiplets. There's the gravity multiplet and the vector multiplet. So when one is writing down the Lagrangian, which is completely fixed by supersymmetry, it turns out that the only choice one has is to choose the number of vector multiplets that one introduces. How many vector fields, how many long-range U1 fields does one introduce? These vector fields come with scalars and an associated moduli space, and they live in the general representation of the gauge group, which means that on a generic point in the moduli space, the gauge group is just U1 to the number of vector multiplets, and then plus 1. And it's a very simple situation. So what I've described so far is just pure supergravity. So if one is just looking at what is the possible data one needs to describe a supergravity theory in 7, 8, and 9 dimensions, it turns out that the only thing that one needs to specify really at the generic point in a moduli space is the number of vectors. It's just these numbers. And so one could write a table for the landscape. How could the landscape look like? From the point of view of effective field theories, you have one effective field theory for each of these values, and naively they all look consistent. Okay. You do not get all of them from string compactifications, and the job of the Swampland is to explain which values you get from string considerations or Swampland considerations. So in this paper in 2019, these authors basically showed that there's an upper bound on the rank coming from Swampland principles, from a version of what is called the Swampland distance conjecture. It tells you that the rank cannot be bigger than 17 in 9 dimensions, 18 in 8 dimensions, and 19 in 7 dimensions. So already from Swampland principles, you rule out infinitely many possibilities. Now, among these possibilities, not everything is realized in string compactifications. So I've color-coded this table according to whether each particular value of the rank is realized in string theory. It's green if it is realized in string theory. It is red if we are sure it cannot be realized in any quantum theory of gravity due to arguments related to anomalies. And the values in yellow are values for which you could, there's no obvious inconsistency from the field theory considerations, but there's no string construction either. So using basically a version of the no global symmetries conjecture combined with supersymmetry, we were actually able to produce a constraint on the ranks of these theories, which changes this table like from this to this. So it changes many entries which were yellow to some entries that were red. In 7 dimensions, there's still a little bit of yellow, which we couldn't explain from this point of view. But in 8 and 9 dimensions, the values of the rank are completely explained, just from Swampland principle, and it's really just coming from absence of global symmetries, in the form of a cobordism global symmetry. So this is already a match between Swampland principles and what you can get from string constructions. But it gets to more than that. What I did before in the previous slide was to describe the situation at the generic point in modalized space. But there are special points in which you can get enhanced symmetries. Okay. So for instance, there's one compactification of string, this is just to give intuition about this. There's one compactification of to 8 dimensions of quantum gravity, which is F theory on K3, that's type 2B string theory with branes in the internal manifold. And one thing that some of the modular positions of the D branes, and they can get close together. And when they do get close together, you get massive states becoming light, a finite number of massive states becoming light, and an enhancement of the symmetry from, let's say, U1 to SU2. Okay. So from these kind of principles, you can actually, from no global symmetries and considerations to the similar to the ones that I was describing before, you can actually make predictions about the kind of gauge groups that can arise at these points in modalized space. And you can, for instance, predict that some possibilities are in the swampland and some others are in the landscape. And by reasoning in this way, actually, from Swampland principles, we could get predictions for what would be the observed global forms of the gauge group in other branches of modalized space, for instance, like CHL string. And so we were able to make a prediction from the point of view for the Swampland for a computation which had not been carried out from the point of view of string theory, and which was later verified by string theory calculation. So the principle of no global symmetries was able to make a prediction, actually, which was then later checked by string theory. So what I described so far is a bit, I told you what the supergravity theories in these higher dimensions are and what is the connection between them and topology. This absence of no global symmetries and this kind of calculations were involving anomalies and connections to topology. But this is a workshop about the connection between the Swampland and geometry. And recently we have also uncovered many connections between Swampland and geometry in these higher dimensional setups. Okay. The idea here is to use the moduli space of supersymmetric objects that are supposed to be in the theory, small instantons. These supergravity theories include gauge fields, and one can consider instanton field configurations, which one can take to become very small, almost point-like. This limit exists because of supersymmetry. Supersymmetry guarantees that this is a moduli space, and you can therefore take the limit. And as you take this small instanton limit, the interesting interaction appears, and the objects that are the small instantons have a work volume theory, which is basically a supersymmetric conformal field theory. Not only they have a superconformal field theory as their work volume, this work volume conformal field theory has scalars, and it has a moduli space. And the geometry of this moduli space is very much constrained due to both supersymmetry and conformal field theory principles. If you take the local geometries which are allowed by these two principles and combine them with the fact that the moduli space of the probe brane should be compact, and this is again related to absence of global symmetries or absence of violations of the Bekenstein bound, not having too many states in a finite region of spacetime, these two things together are enough in 8 and 9 dimensions to amount to an exact reconstruction of the bulk moduli space, by which I mean that the principles that one gets from combining the solutions that one gets by combining these two principles only allow for a finite number of possibilities. And this finite number of possibilities actually matches the different possible geometries of the bulk moduli space that one gets from string theory constructions. Once one has this point, basically it's possible from this geometry to recover all the data if the supergravity at massive level. So for instance, to give you an intuition of how this works, in some cases you might conclude that the geometry of the moduli space of the probe brane is a hyperkähler manifold, and the only known compact hyperkähler manifolds are T4 and K3. So that leads to two of the possibilities in the list of string compactifications. This is a very general principle, and it's gotten to the point that once one recovers the geometry, you can get everything about the theory in 8 and 9 dimensions from these general principles. So in principle, you could say that you have achieved the string-Lampos principle in 8 and 9 dimensions. With just one caveat, we are able to get everything involving massless fields. All the story that I described so far was about degrees of freedom becoming light at points and so on and so forth. But we are still to understand what happens systematically in a universal way to the massive states. So for instance, in a string compactification, you have the supergravity fields, but then you have the Kaluza-Klein modes or the string modes. How do we understand those systematically? And that's a question that involves geometry, which has been analyzed recently in papers by Lee, Lersch, and Bagan. And a related question, perhaps, is which I find very exciting, and I'd like to throw out this is really an open question, which is very interesting, which is the question of whether it's possible to have more than one quantum gravity or more than one string theory compactification with the same number of massless degrees of freedom, the exact same effective field theory at the massless level. Okay, there's some evidence, for instance, that there might be discrete choices involving the construction of M theory in 11 dimensions. So if this thing is true, for instance, there will already be a choice at 11 dimensions. But more generally, one can ask the question: is it possible to have two quantum theories of gravity that are the same at the massless level, but they differ at the level of massive states? I did say I wanted this to be an interactive review, and I will be throwing in questions for the audience at one point or another. And this is the first such point. So if anybody has any thoughts on this, I'd love to hear them. Can anybody come up with an example where you have the same low energy effective field theory, but the string theories are different at the massive level? Oh, Kumran thinks there are.
Someone believes that there are.
I have to remind myself, but I have the recollection that there are examples. I will think about it.
Okay. I mean, it's just this is just to get the ball rolling.
Miguel.
Yeah. Hey, Luca.
Hey, can I ask you a question about the previous slide?
Yes, please.
So when you say the compactness of probe branes, do you remind a specific class of probe branes or any probe brane?
No. I do have a specific class of probe branes which with high enough codimension. Okay, with low enough codimension, this is not the case. And for instance, okay, the way you argue for this is with stuff like the Bekenstein bound. You basically argue if you have a high enough codimension brane for which this was not true, you construct infinitely many states in a finite region of space, and that will lead to a violation of entropy bounds. If you try to do this with low codimension branes, for instance, because of the gravitational back reaction is huge already at infinity, there's no analog of the Bekenstein bound. So for instance, this wouldn't apply to D7 branes.
So one example, Miguel, that might be a counterexample to that statement about the massless modes is that, say, for example, you take toroidal overfolds, let's say with a Z2 times Z2.
Yes.
And suppose you choose a Z2 times Z2, which has no fixed points in the joint Z2s, that you have such choices.
Yes.
But you cannot turn on discrete torsion with that Z2 times Z2. So that's an example, I assume, that because changing the sign in a sector which has no massless modes does not change the counts of the massless modes.
Do you have a construction in mind where it's clear that you're not projecting out some cycles as you do that as well?
Well, the difference between putting plus or minus shows up in a sector with no fixed points. Therefore, it does not affect massless modes.
I see.
But to call these different string theories would be a little suspect, of course, because I mean, it's a discrete theta angle, as you say. So in this case, you just say that turn it on or off in that case.
That's right. Exactly. So Kumran just gave an example where the theta angle or this discrete parameter is very geometric. And the question is to understand this kind of things generally and also in higher dimensions. But I think that's a good example.
So I think I also know an example, to interrupt you. So if you take Gepner models describing K3 compactifications, so there's a number of like 20 or 30 of them, and they all have the same massless spectrum, but I adopt that they have really identical partition functions.
Which models, Ralph, sorry?
I say Gepner models describing K3 compactifications. There are a couple of them that gives you K3, I mean, the massless spectrum on the K3 that you expect, but I adopt that the partition functions are equal for every.
I see. So they differ at a lot of massive states.
Class, I think.
Do those examples, Ralph, are not connected by changing moduli?
So this could happen, but still, yeah. Okay, no.
Because that would be very surprising.
Yeah, of course, yes.
That would be extremely surprising.
The same moduli space. I see your point. Yes.
I think we would have known about K3.
Yeah. Sure. Got your point.
Exactly. If they are in the same, exactly. So that's part of the question. So if they are in the same moduli space, you perhaps wouldn't count them as separate. And then, so that going back to Kumran's example, right? I guess your example has 16 supercharges, but if it had 8, it would be like an orbital Calabi-Yau, and then there's a possibility that it would be connected via, topology changing transitions to any other.
Yeah.
So it's difficult to make sure that
connected. Yeah, I guess they are connected.
Yeah.
Yeah.
It's difficult to make sure in any of these examples that the stuff that you're doing is not connected. And if it's connected, they have the same theory. Really, they're just different corners of the same beast.
Yeah.
So that's just an interesting.
Then sorry, Miguel. My other question is, what do you mean by different string theory?
Right. Oh, sorry. Yeah. Okay. So I mean, when you have a right. Sorry, that's probably an abuse of language. I probably should have said different string compactification. Different model of quantum gravity in D dimensions. Model of quantum gravity in D dimensions is given by the set of states. Different tower of states. So if I'm calling two things different if they differ either at the level of massless fields or at the level of massive fields of their interactions as a D-dimensional quantum theory of gravity.
Okay, thank you.
Okay, very good. So that's one thing. And this question about massive states can be attacked by something called the covariance conjecture. So the covariance conjecture is a particular generalization of the no-global symmetries conjecture, which is more on the topological side of things. So I don't want to talk too much about it, but I think I've thought a lot about it, and I think it's very interesting. So I felt weird not to mention it. So the covariance conjecture follows the reasoning of the absence of global symmetries to symmetries involving topology change in spacetime, and the conclusion that one reaches is that if the covariance conjecture is true, every quantum theory of gravity in any dimension admits a boundary condition. A boundary condition in the same sense that condensed matter materials admit it. A boundary where the universe ends, the end of the world. And you can get interesting Swampland constraints by studying the physics of this end of the world brane. So there's fun connections between this and anomalies of direct topology, key theory. The one thing I want to flash to the more mathematically minded members of the audience is that there's a very strong interplay between coordinates calculations in algebraic topology and this point of view of covariance and quantum gravity. So it's an interesting arena if you're interested in algebraic topology as well. So that was the weak gravity conjecture. So that was the no-global symmetries conjecture. Now let's go to the next, perhaps most famous conjecture, the weak gravity conjecture. The weak gravity conjecture is a statement not about the massless fields per se, but about massive charge states. It's telling you that in any theory, in any quantum theory of gravity, which has a long-range U1 gauge field, there has to be a particle whose electric charge is bigger than it's actually lower than its mass in Planck units. For such a particle, the electromagnetic interactions are stronger than the gravitational interactions. So that's why it's called the Weak-gravity conjecture. The Weak-gravity conjecture, you can apply to the real world and happily find it satisfied. It's satisfying the real world by electrons, and it's related, and some arguments supporting the Weak-gravity conjecture is related to the kinematics of black hole evaporation. One can work out that if one has a charged black hole with an extremely charged black hole with as little mass as possible given its charge, then the only way it can decay is if in its near horizon region, which I drew here, which has a very strong electric field, charge carriers are produced by pairs in such a way that you emit the charge carrier and it can discharge little by little. There's a kinematical condition for this process to work, and that's precisely the Weak-gravity conjecture. So it's somehow related to the physics of black hole evaporation. Why do we believe that the Weak-gravity conjecture is true? Well, there's lots of evidence from the fact that it's true in every string theory compactification. You can prove it in perturbative string theory. The argument was already even hinted in the original paper. You can actually, with some caveats, prove some version of the statement in holography. And in many cases, with additional assumptions, you can prove it from various techniques coming from unitarity and positivity bounds in low effective field theory. Weak-gravity conjecture could be an hour and a half long review talk in itself. And fortunately for me, a lot of the work to keep you up to date has been done recently. Since last week, there's a comprehensive review by Harlow, Heidenreich, Reis, and Rudilius. It's a very good review. It surveys all the variants of Weak-gravity conjecture, all the different statements, and so on and so forth. So I urge you to check it. It's just last week on archive by these authors. So the Weak-gravity conjecture. Let me give you one slide about the phenomenological implications of the Weak-gravity conjecture, or at least some of the implications that got a bunch of us excited about the Swampland program in the first place. The Weak-gravity conjecture perhaps is not very much constrained to the standard model because it just tells you that the electron has to be light, and you knew that before the weak gravity. But it certainly can put constraints on models of newly charged matter and models of natural inflation. So, for instance, in models of natural inflation, you have the action, which is the infloton is an action, which is a periodic scalar, which receives a potential for non-perturbative effects, and these non-perturbative effects, they themselves should obey a form of the weak-gravity conjecture. So potentially, it can put upper bounds on cosmological observables. There are many caveats in making this story work. There are uncontrolled factors and so on and so forth. But it really hints that it really gives a proof of principle of the fact that quantum gravity can say very interesting things about inflation and cosmology via Swampland statements. Okay, so that was the two-slide review of the weak-gravity conjecture. I'll be talking more about it, but in relation with another conjecture, which is perhaps the one that has the strongest connections to geometry, and that is the distance conjecture. Okay, what does the distance conjecture say? Well, in string theory, one often has massless or very light scalar fields, which we call the moduli. They control things like the shape of the internal manifold. They control the couplings of the theory. And so you talk about the moduli space of the theory. And often you can work out what is the geometry of this moduli space. There's a natural metric on it given by the kinetic terms of these scalars. And this metric often has points which are at infinite distance. It is not the metric on a compact manifold. There's unbounded regions. And you can study these in one or another string example. And what one finds is that it's a very interesting observation that as you get close to any of these infinite distance points, many states become light with respect to the Planck mass and start running in loops, and they start lowering the cutoff of the effective field theory in such a way that by the time you get to infinity, you could say that they have renormalized and Planck to infinity, so there's no gravitational interactions there anymore, or that the effective field theory has completely broken down at any given finite energy scale. Okay? So that's what moduli spaces are, and this is a feature that you observe in every string theory compactification moduli space. And the distance conjecture tells you that this observation actually is pervasive. It happens literally in every infinite distance limit you might find in moduli spaces in string theory. Okay? There is a very interesting connection between the distance conjecture to the conjectures that I described before, absence of global symmetries and the weak gravity conjecture, which is that in this, it seems to be true as well that in every infinite distance limit, some gauge coupling goes to 0. And if a gauge coupling is going to 0, that means that one is recovering a global symmetry. But global symmetries are forbidden in quantum gravity. At the same time, it doesn't make sense that you gauge or break a symmetry. So it's not like these symmetries can be broken, kind of like by continuity in the infinite distance limit. So something else must happen. And what happens is that as you get to this limit, the theory, the gravity decouples from this theory. M Planck goes to infinity units of the cutoff. So that's an interesting connection between the two, between no global symmetries and the distance conjecture. And you can even say more. In principle, there could have been a limit in which the gauge coupling that is going to 0 is not associated to a theory of particles, but to a theory of strings or membranes or something. In all examples that we observe, the gauge coupling that is going to 0 is the gauge coupling of a 0-form global symmetry, or sorry, of a 0-form gauge symmetry or a 1-form gauge symmetry. That means that either an ordinary vector gauge field is having its gauge coupling into 0, or two-index antisymmetric tensor, like the B-field in string theory, has its gauge coupling going to 0. Those are the two possibilities that we observe in every limit. And relatedly, when you see what this means in the string compactifications, that means that the charged object is a Kaluza-Klein tower for the 0-form case. So it's you're basically decompactifying, or some fundamental string whose coupling is becoming weak. So that's the idea of the emergent string conjecture. This is indeed that the two things that are happening, you cannot have something like a membrane becoming light. And I think we're going to hear something more about this in Timo's talk. Also, one can prove that since one is recovering a global symmetry, at least with some supersymmetry, this tower of states is becoming more and more stable. More and more states of the tower are becoming stable asymptotically as you get to the infinite distance limit. And this is the subject of Aaron's talk. Then, on top of all of this, there is an intriguing connection to the physics of action strings, at least in 4 dimensions, in modalized species that arise from Calabi-Yau compactifications in 4 dimensions. So it turns out that in these cases there are some objects that can realize infinite distance excursions in a finite region of spacetime. They're codimension to strings. And you can relate properties of the tension of this string, or whether the string is satisfied with gravity, to properties of the infinite distance limit and the tower of states. And I think Luca is going to be talking about this in his talk. So this is bird's eye bit of what is the distance conjecture and what is the proposed connections. Has many connections. There's a lot you can do because it's intimately connected to geometry of string compactifications. And in particular, there's one thing that one can do, which is actually one needs to do to basically prove the Swampland distance conjecture in complex structure modalized space of Calabi-Yau compactification. So this is a very general setup in which there's a proof of the Swampland distance conjecture using the theory of asymptotic mixed host structures. The basic idea is that the central charge, which is related to the charges of BPS states are related to their mass. They're related to the central charge, and these central charges have, which in principle one needs to get by solving very complicated equations, actually have universal forms around the infinite distance limit. And around each infinite distance limit, it turns out that there is a monodromy of infinite order acting on these periods, which means that if you have one BPS state, you get another one with twice charge, and another one, another one, another one, all of which are going to 0. And the gauge coupling is going to 0. Okay, so here we have a context, a particular context in which we understand precisely why these tower states are coming light, and it's very general, but it's not completely general. So another question that I wanted to throw into the audience, and I'm sure we'll discuss it more in the rest of the workshop, is how much of this structure is quite general? What is the underlying geometric structure of quantum gravity modalized spaces? And there's been proposals like domestic geometry by Chakotay, and more recently, there's the proposal of tame geometry by Thomas Green. And one possibility which I find very interesting is that both noticed by Chakotay and Green is the fact that the modalized spaces that you get in the string compactifications, they have metrics of negative scalar curvature, and the infinite distance limit look a lot like the holographic boundaries in the ordinary area CFT correspondence. So perhaps there's some way to understand the bulk of the modalized space coming from the boundary in a way similar to holography. So if anybody has comments on any of this, certainly a lot of people here know more about this than I do. It would be a great time to chip in.
Well, I think one question is, do moduli spaces even exist away from n equals 2 supersymmetry? Because if they don't, then I think the whole structure covers every single possibility. So yeah, and it's very difficult to find moduli spaces without extended supersymmetry, I think, to my knowledge.
That's right. That's right.
So this question is not clear what examples one is considering in these questions. Yeah.
Right. So one could consider situations where there's some sort of hierarchy between some fields which, even though get a potential, are still very light. So this is still a kinetic terms for them and some notion of geometry.
Then it's not a moduli space.
It's not a moduli space. It's
not a well-defined problem so much.
You're completely right that I should have perhaps emphasized a little bit more than the reason why one focuses on these kind of things is not just that, you know, there's the exact moduli space that you can understand. That's the first step where you can understand everything right. But eventually you're interested also in understanding things with a potential a little bit, right? So there should be some sweet spot between having some sort of a scalar potential and still having some notion of geometry for the scalars, perhaps. And then the question, if I go to infinite distance points for these few scalars, that's a well-defined question.
Well, I think with the potential, infinite distance points are not so well-defined because of,
because they can diverge.
Yeah. But anyway, with regard to moduli space, it's not clear to me if there are any moduli spaces.
Well, also to be fair, there can be situations where the potential makes sense, or the configuration with approximate moduli makes sense asymptotically, but not everywhere. So for instance, think of the SO16 non-supersymmetric string in 10 dimensions. That one has a scalar.
Those limits would be ones where you restore extended supersymmetry usually. So I think,
but in this limit you do not.
Anyway,
right?
Okay, it doesn't. Yeah.
A few weeks ago, there was an interesting paper claiming evidence for a conformal manifold in a non-supersymmetric CFT. The trick there was to use an S-fold. So the supersymmetry breaking was global rather than local. It was a paper by Emanuel Malek, Trigante, I forgot the full list, sorry.
I see. Was this in more than 2 dimensions?
The CFT was a set of ADS4 vacua dual to CFT trees.
Very interesting. Very interesting. I didn't know about this.
Ivano also put a question in the chat.
Yes, hi.
Hi, Ivano.
Hi, nice to see you. So I was just asking regarding this discussion with Eran about, you know, how to generalize distances away from exact moduli spaces. And there is this notion of a couple of different notions actually of metrics defined back in the 90s that were revisited by John Stout recently, if you remember his paper on these quantum information metrics that could in principle be used to define distances in theory spaces, you know, more generally. I was wondering what you thought about this. If one could reformulate some sort of distance conjecture for these.
So I think what John was doing makes a lot of sense. I'm not sure you can. So there's certainly a notion of metric that comes from that. the question is whether you really recover like the tower of states are becoming light. So he can recover their singularities and so on and so forth. I'm not sure he can recover exactly the distance conjecture, even for the case of modalized spaces, right? And for the other cases, I guess is what Aaron is saying, right? Like really, the obstruction is coming more from the potential than the kinetic term itself, right?
Exactly. And in those cases, you would have this theory space which is spanned by the couplings that appear in the potential and stuff like that. Like it would really be a holographic metric, actually, because it's defining field theory. So you would need to have some holographic setup. Then you have your holographic field theory with no gravity, and then you use the quantum information metric there.
I think that the really nice point about John's work is that it gives a very physical operational definition of what it means being at finite or infinite distance, right? Like it's about distinguishability of measurements. That's what the metric means.
Miguel, okay, I think you have perhaps a little bit less even than half an hour or half an hour. So depending on how much time you want to spend on this question, you should continue.
Yeah, I think we're fine. So there's a bit more I need to talk about. But I think it's important that we have discussion.
Yes, I agree.
Thank you anyway for the answer.
Okay, let's get going then. So why do we care about the distance conjecture if you're not if you do not love n equals 2 configurations, or as Aaron was saying? Well, that there's important phenomenological implications. Particularly in the context of inflation, because when you have if you believe the distance conjecture, it's telling you that whenever you traverse any trans-Planckian field range, there's some tower of states becoming light. And when the states become light, they are very bad for your effective field theory. And the whole point of inflation is to having a kind of large field excursion without too many states becoming light. So this can be, having a large field excursion within the same effective field theory. So you can use the distance conjecture where the states go down exponentially and at some rate alpha to upper bound the kind of field range that one can get during inflation, depending on what the values of this coefficient alpha are, okay? So it's really important to find out what is the smallest possible value of alpha, because this is really a quantitative prediction, right? Here you would put like the Hubble scale or during inflation or something, and this really gives you it's a quantitative prediction on what is the field range that we can observe, and that translates to precise bounds on experimental things like the tensor to scalar ratio that people can measure. So it really is important to find what is the smallest possible value of alpha. So for instance, using the theory of mixed cost structures, it seems like alpha is lower bounded by 1/√6. And so that's why we care a lot about the distance conjecture from the phenomenological point of view. And here I wanted to throw in another question that I have, which is more on the phenomenological side, which is like the basic logic of bounds like this, or saying that the distance conjecture gives an upper bound for inflation or can constrain inflation, is the idea that the tower of states it can be when it becomes light, it completely screws up the inflationary effective field theory. But I wanted to hear people's thoughts about whether this is really the case, because it could be that the tower of states that is becoming light is not coupled to the dilaton in a very strong way, perhaps. The distance conjecture says little about the nature of the coupling to the tower of states. Or even if the tower of states becomes light, maybe you can still have like that nice scalar rolling down a potential, down an effective potential. So
I do not understand that, Miguel. You're saying that the mass goes exponentially, so therefore there's a direct coupling to the mass. Mass is this term you see in the action, so it's a strong coupling.
Yeah. No, that's true. So so if there's like a gauge coupling going to 0 or something like that, then it's true that the massless field couples very strongly to the scalars. But for instance, Kurman, think about again the SO16, SO16 string, right? There you have all the massive states of string states that are becoming light, and still you can compute the potential exactly. And okay, it's not flat enough, but it could have been. There could be a situation where even taking into account these quantum effects, the potential is very flat. I'm asking if that is obvious that cannot be ruled out.
I'm saying even if it's flat, the fact that it couples to them means you can produce these light states. That's the usual problem, I thought, with inflation, right? I mean, as soon as you start rolling, these are light states, and you're going to create them and messing up inflation. That's what I thought was the problem.
Right. But the coupling is also going to zero. So there's two. Okay, but that's a good point, I think.
Yeah, Robert is saying.
Oh yeah, the light states could then dominate the energy density. But Robert, doesn't that also depend on the coupling? Like this, it's like there's two competing effects. The states are becoming light, but also their coupling is going to zero. So the inflaton is less and less likely to decay into these states as it goes through.
But the coupling, I mean, from the weak gravity conjecture, we know the form of the relation between mass and the coupling, right?
Yes, that's right.
So if you use that, then I think that will already mess it up now.
I see.
You can't make G sufficiently small without mass being small.
Robert is also saying that for that, you need to have inflation, to get inflation started, you need to roll a distance. Okay, well, anyway.
Maybe you can have something that is not inflation, no? But if you want to keep an Einstein gravity description, I mean, the cutoff is getting lower and lower. So at some point, it's pushing the Hubble scale lower and lower and lower. And then it depends what type of inflation model you want to have. If you want to have an observable tensor to scalar ratio, then you cannot have it. If you want to have small inflation, small field inflation, maybe you can have it for some time.
I see. So the point is that you would couple too many of these states. You would produce too many of these states during inflation. That's what you're both saying. Okay, let's get going then. So the distance conjecture also leads to predictions about the black hole extremality bound. So it's a simple argument, but it's very nice. The weak gravity conjecture tells you that the charge to mass ratio of a particle, I wrote it had to be bigger than the gauge coupling, but in general, the argument related in the weak gravity to evaporation of black holes suggests that it actually should be bigger than the charge to mass ratio of an extremal black hole. And that depends on, it's a theory dependent number, and it's called the extremality bound, and it's a quantity you can compute in one theory or another. So it's a coefficient you can compute in some cases. And because the tower of states in the distance conjecture is the tower of states which is charged under this gauge coupling, the distance conjecture also leads to predictions about the black hole extremality bound and vice versa. So that's basically the distance conjecture in a nutshell, and most of the support that we have for it, unlike for the other conjectures, is really empirical, coming from string theory. There are cases like the complex structure model space where you can just prove it, but there doesn't seem to be there are not too many arguments related to black hole physics that support it. So in a recent paper with Yuta, Irene, and Kumrum, we gave a black hole argument supporting it in limits where some gauge coupling vanishes, basically making sure that the effective field theory description made sense and you were not violating Bekenstein's bound, so not having too many states in a given region could give you something like this, would give you something like the distance conjecture. But it would be interesting to know if one can make a more general argument. And in this line, I think that perhaps the most promising set of ideas is so-called the emergent proposal, which kind of turns the distance conjecture logic the other way around. So in the distance conjecture, you say there's an infinite distance limit and a tower of states becoming light. The emergence proposal says that there's an infinite distance limit because there's a tower of states becoming light. So what it shows is that when this tower of states is charged, you can compute the loop corrections to the metric coming from this tower of states, and they very much look like the metric you do observe in the moduli space. And it's just the fact that you have a tower of states that's enough to produce an infinite distance limit where the gauge coupling goes to zero. This is a very, I think it's probably, in a sense, there's subtleties to make it work really precisely in some cases, but it's probably, I think it's close to the reason why distance conjecture is true. So that's the distance conjecture, and the distance conjecture is all about what happens asymptotically in moduli spaces. But it's also interesting to think about the other limit. What happens far away from asymptotic corners? What happens if you go as far deep into the bulk of moduli space as possible, as far from the boundaries as possible. What does the physics looks like there? So we initiated an exploration of scenarios like this in this paper with Cody, Kunrum, and Irene, and you know, we were basically at those points which are kind of strongly coupled. Everything is heavy. You expect that the lightest states are BPS states, so that's what we studied, the masses of BPS states, and these points deep in the bulk in the moduli space are very different from asymptotic points where tower of states become light. Here, there are points where typically you would expect there's the massless fields, which are protected by supersymmetry, perhaps, and then a gap up to close to the Planck scale. And so that's basically what we find, but we find some interesting correlations. For instance, so for toric Calabi-Yau, what we find is that as you increase the number of massless fields, the cutoff of BPS particles goes down, which is kind of what you would expect according to something called the species bound. I didn't want to draw too much attention to this, but just to point out that we still need to understand what happens deep at the bulk and moduli spaces. They are very, very interesting points, and there's things that one can say about them. Okay, so we were talking about the metric moduli space, and the next thing that we want to do is to understand what happens when there's a scalar potential, right? So what does it happen? What happens whenever there's a non-vanishing scalar potential in string compactification? Well, typically, what one always finds by studying different limits is that the potential goes like a power of some mass scale, and that mass scale is the mass scale of the tower states associated to the distance conjecture. Whenever you have limits in which you can access things asymptotically. Okay, so limits where the potential goes to 0, like the SO16, SO16 example I was describing before. You can do this in several ways. You can do it because of one loop effects, Casimir energies that generate a potential, or you can do it perhaps because you have flux compactification. You turn on some fluxes into the internal manifold that give you some potential. But in both cases, the potential goes like this. And if you combine this with the distance conjecture, which tells you that the mass of the tower states goes exponentially into the potential, you get that the potential itself goes asymptotically satisfies a bound like this, where C is some order 1 number. This statement, which seems to be, it's basically, if you assume this kind of conclusion, this kind of scaling, it's true in every asymptotic limit because of the distance conjecture, but in any case, experimentally true in all these asymptotic limits that we've been able to explore with string compactifications, is the no-de Sitter conjecture. And it's telling you that there's no-de Sitter vacuum string theory, okay? It's a statement which, when you argue it like this, it's a statement that holds true asymptotically. There's not that many ideas that suggest there might be de Sitter far away from asymptotic limits, that there's no de Sitter far away from asymptotic limits. Although there's the TCC bound, which provides an upper bound on the lifetime of any de Sitter-like solution anywhere in the bulk of moduli space. And it's perhaps not as rigorous as some of the Swampland conjectures. And the real solid support for it comes from arguments that work in parametric regimes. But in any case, it's a conjecture which has been extremely useful because it's triggered a lot of progress. That's forced people to look more rigorously at pre-existing constructions, which perhaps were often accepted not as critically as before. As an example, I will describe a little bit something that has happened recently, which is what is called the tadpole conjecture. And to do this, I will first describe the existing constructions for de Sitter in string theory. The uplift constructions, I will just do one slide, very simple, very quick argument. Okay. So Daniel, I think you have a comment in the chat. So Daniel has a comment that the Dine-Cipher problem can be avoided though if there are unbounded fluxes. Right, perhaps this ties in with the tadpole conjecture because fluxes cannot typically be unbounded, or do you think like the GKT like well, anyway.
Sorry. Yeah, I just wanted to comment on the point you made on the last slide. Nothing too deep. Just wanted to say that in general, it's not clear that asymptotically the potential needs to be dominated by one term, because in some cases, not all fluxes are always bounded by tadpole conditions, especially in type 2a. So I think one has to work harder to show that really de Sitter at large volume and small coupling is forbidden, which I think it is, but
got it.
Yeah.
Okay, thanks. Okay, so
it's also interesting there that we have proposals that violate this runaway in ADS when the energy is negative, but there is no proposal for positive vacuum energy, even with unbounded fluxes. I don't know what's the difference between both.
Yeah, actually, I think I had a paper like maybe 4 years ago where I showed that this basically doesn't work. So,
yeah,
but
exactly.
you have to really look at the flux potential and check what's going on there. But you can never have, at least in type 2a, can never have de Sitter just using like large fluxes and then sort of balancing different terms at large volume and small coupling.
Yeah, even beyond the weak coupling point that you studied. I mean, it seems to be true more generally.
Okay, so let me describe a class of existing constructions of de Sitter in string theory, which is uplift constructions. So you would first take some Calabi-Yau, which has n equals to supersymmetry, and then break to n equals 1 or to n equals 0 by including orientifolds and fluxes to find a suitable four-dimensional ADS vacuum. Now, one has a scale-separated ADS vacuum where there's a tiny cosmological constant compared to any effective field theory scale in this model. You can hope to find some small effect, like some small effect like an anti-brane or high relative corrections that would actually shift this small vacuum energy from negative to positive while not spoiling control of the solution, thereby obtaining de Sitter. Okay. Now you would expect that if you're able to do this in one particular solution, you cannot control what the value of the vacuum energy that you get is. Maybe it's very large, but if there is a large set of solutions where you can do this, then perhaps you can find a situation where looking at the class of models between steps 1 and 2, in which step number 3 works. Okay, so that's the basic idea of uplift constructions of de Sitter, and I just wanted to make so the tadpole conjecture. It's in a sense you could think of it as related to an observation that number 2 is way subtler if one wants to do it in a systematic way, producing a landscape, producing many solutions. Okay, so what did the authors of the tadpole conjecture? What does the tadpole conjecture state? It's a more concrete statement about complex structure moduli in type 2b or F theory, and it's saying that with a large number of complex structure moduli, turns out not all of them can be stabilized with fluxes. In general, perhaps there are special points which with enhanced gauge symmetries where this can happen. The idea is that this cannot happen in general, so there cannot be, in any case, even if it can happen in particular examples, it's unlikely that a large landscape exists. So to see how that happens, for instance, in one of the examples that they studied, which is F theory in K3 times K3, there's two competing effects that one needs to fight. So on one hand, you need to turn on fluxes to generate a scalar potential. So you need to turn this flux to turn a scalar potential for the complex structure moduli, and you need to turn enough legs of the flux so as to generate a scalar potential for all the complex structure moduli. But at the same time, which happens to be around 1/3 of the total number of moduli when they studied in this example. But on the other hand, one also needs to satisfy this tadpole constraint in F theory, which at large H3,1 grows like H3,1, which is the number of complex structure moduli over 4. So that means that these two statements are actually incompatible, and asymptotically, except perhaps at particular points, it's just not possible to stabilize all the moduli while solving the tap. Okay, so I guess that a nice set of questions that we were actually already discussing in the Rimberg workshop.
If I may interrupt, I apologize.
Please.
I found what you just said too strong. I mean, you said general points and so on. But really, if you switch on fluxes and just count the points where you switch on fluxes and you expect vacua, it's not clear that this is still not true. It's just that maybe generally, maybe in many cases, you get some moduli stabilized at singular values, such as certain three cycles have shrunk.
Yes.
But that doesn't quite tie in with your statement that the landscape should basically
Very
go
good.
away.
Yes. Yeah, absolutely.
And also, quite generally, I mean, it's the tadpole conjecture, as I read the original papers, did not say that. They said that it cannot be done at a smooth point, at a generally smooth point.
Very good. Yes.
But then it is constantly quoted as saying that there's no landscape. I mean, maybe there is no landscape, but it's not what the authors claim. Maybe the authors want to claim that now. I'm happy to do that for them. But
let me put it like this: there's either no landscape, or you're predicting probably tons and tons, because at this singular points you typically have enhanced gauge symmetry. You have additional massless fields.
Of course. If you have conifold, for example, you can have a conifold point where three cycle shrinks. There are extra light states there.
But if you have 100 moduli, you might have 100 gauge fields.
Of course, why not? Sure. I mean, sure. I don't see a priori the reason that this is promoted to saying there's no landscape.
Okay, I think that's a fair point. It raises more issues about control, though, right? Because then you have like 100 massless fields, and then you need to explain how they're not coupled to other stuff. But I agree with you. I see your point. This is what I said. It's perhaps a special point in house case.
We do have 100 fields in standard model of the order of, right?
No. We have 100 degrees of freedom, not 100 U1 fields.
Yeah. Okay. Good. Fine. Okay. But then in the MSSM at least you have many more.
A few more.
Can I also say something very quickly to this?
Please.
It's just, I mean, like, it's in the same vein as what Arthur was just saying. It's, I mean, there are also these are just examples, but there are these Calabi-Yaos which have something called green placer symmetry, where you can manifestly basically show that by, say, turning on fluxes for two complex structural moduli, you can fix 270 in one example I know of the other ones, because the periods depend at higher order on all the other ones as well. That's a subset of all Calabi-Yaos, but that green placer symmetry probably is there, and then you don't even need to sit at a conifold point.
Very good. So that brings. I think you guys are actually going through the questions I wanted to ask here, which is like, how general is this kind of statement? So it's kind of what you're saying now, Alexander. Like, some Calabi-Yaos have this, but you want to have a very large landscape, so on and so forth. So,
yeah, but I mean, like, we know that a whole I think a whole certain part of the so-called CCs have them, and like, you know, I mean, the search for Kreuzer-Skarke, I think, for instance, hasn't been really done to like, or maybe it's done by the Cornell group. I don't know whether they look for these green placer kind of like manifolds, but they have this kind of structure. But you know, we have only the tip of the iceberg ever searched for that. I mean, even if the fraction is only like 1% or 1 per mil that have this thing, I mean, like, you know how many Calabi-Yaos are there in Kreuzer-Skarke? I think their current estimate is 10 to the 300.
Well, that's the point. That is precisely the point. We are, until we figure out these kind of things, it is very far from saying that we can do this kind of thing in a control setup. And the de Sitter conjecture kind of like reignited this debate. Like,
that I agree, but the point is that, you know, I think I tend to agree with Arthur. I mean, like, the tadpole conjecture made a certain statement for the smooth point. You cannot take it as ruling out the landscape as a whole. It's far too strong. I mean, that's not possible. We don't have the information to make such a statement.
Right, but it certainly points out there's a subtlety which was perhaps not taken into account. It was not obvious from the original discussion. So it's already improved the original discussion.
It motivates further, more explicit searches. Let's put it like that. Yeah, I agree.
Definitely, we need to figure this one out.
Can I?
Yes.
Sorry, can I make one quick comment?
Please, Eric, please.
So since Arthur and I think also Alexander mentioned the conifold point, you can run a line of argument and arguing that also if you approach the conifold point, that you expect, if you want to stabilize moduli close to the conifold point, you would also expect the tadpole charge, the flux number, to increase. So I mean, there's no proof, but there are indications that also that happens there. So it's not just, oh, you go to conifold and then things are fine, but also at the conifold, you have to check that your flux number is not blowing up.
But I'm sorry, I'm confused. At a conifold point, I don't know. I give you one flux. I mean, in the end, I need only two pairs of fluxes, basically. If I look back to GKP, and if that manifold with a conifold point, in particular, the example they give in section 4 or 5 there with an F theory lift, I think is one that probably has this Green-Placer symmetry. Then all the period of this pair of this A and B cycle pair depend at higher order on all the other whatever order 100 complex structure moduli. They all get frozen, and these two pairs of fluxes. I mean, you can pick numbers where then the total M times K tadpole and the contribution is maybe of order 100. It's not that big. I was trying to make a statement, genericity argument, that if you take a very general point of view, you could run an argument that if you go to boundaries in moduli space, that the flux number will increase. Now there could be special situations, and maybe the one you're mentioning is one of those. But but you see, for the existence of a landscape, a certain specialness in the sense, as I said, of a per mil fraction of all Calabi-Yau's, or even a tenth of a per mil or a 10 to the -6 fraction is probably enough. It's just enough.
I think
you see, in order to turn a conjecture into a statement, you have to prove it for all.
But Alexander,
otherwise it's not
Alexander, I think the fact that we're having this discussion proves the point, which is that there's a much subtle issue here than was appreciated perhaps before, or maybe it was appreciated by some people. For sure there was, but it's on the table now.
Miguel,
I agree. With that, I agree. I mean, and I agree it's worthwhile searching and finding more explicit examples and doing that. I agree with that. I'm just saying, that it's rare doesn't mean it's not there.
It's not just worthwhile, it's important.
Okay. For me, worthwhile and important is the same.
Miguel, we are almost entering the discussion time now, so
yes. Well,
sorry for interrupting.
No, but but Dieter, the idea was originally that part of the discussion was very much embedded into the.
That's fine with me, but I just want to tell you that the 90 minutes are basically.
I know, and we're good. Because I'm basically getting to the end. Actually, there's just one more thing, one more other issue that I wanted to bring up, and for this one, actually, I suggest we don't discuss that much because there's going to be a dedicated discussion about this topic tomorrow. Which is related to constructions, constructions of the sitter. In this 4-step procedure that I described, step number 2 was find an ADS vacuum which was scale separated, and even doing that, even just forgetting about the sitter not anymore, just thinking about scale separated ADS is a very interesting, very concrete, very sharp question for which there's still ongoing debate. Which is, are there large parameter families of scale-separated vacua in string theory? The debate is often focused, there are several proposals, but the debate often focuses on the most concrete and most controlled proposal, which is the DGKT proposal, which is an ADS4 vacuum, the compactification of massive type 2A string theory, which it's a solution you can find in a 4D effective description. So you just take the general Lagrangian two-dimensional reaction, which is quite complicated. But you do it, and then you find this large parameter family of solutions. But it turns out, so far, there's not completely waterproof that there's a fully back-reactant 10-dimensional geometry solution. Okay, a bunch of people suspect that such a solution does not exist. So there's a lot of work on this, and we have this discussion tomorrow. So, for instance, it was a related recent paper by Collins, Jeffries, Banff, Xu, and Yao. They show that it's not really in many examples the scale separation you can find in DGKT is absent for no apparent reason other than just the fact that geometric properties of manifolds are such that this happens. So I urge you to check out the discussion tomorrow. And since I'm giving the review and I have like the spotlight for a moment, I'm gonna use it. To push an observation, which I find fascinating, and I think it's quite polarizing. I talk to people, and they either think it's amazing, or they think it's nothing. It's the opposite. There's no middle ground about this, which is that it turns out that if you study there would be, assuming this vacua exist, there will be a dual conformal field theory, and you can compute the dimensions of the operators dual to the light moduli that you could find in the GKT, and the relationship between masses and the bulk, which is what you compute from supergravity, and the conformal dimensions is a quadratic equation, complicated quadratic equation like this. It turns out that the masses that you get in the GKT are such that the deltas you get from this equation are all integers. They are not, it's not just that these masses squares are integers, it's just deltas are integers. They are precise integers for the square masses, just that these things are integers. And this also happens in other models in which there's proposed scale separation. So I think that certainly maybe it has a deep explanation or something mundane. In either case, I'd like to know what the answer to this point is. So we've come to the end of our hike, where we focus on the more geometric side of the Swampland program. But there's a lot more to the Swampland and the ideas that we sketched here. So we basically didn't have time to talk about the Festina lente bound, dynamical covariatisms, the gravitational mass conjecture, the species bound, the idea that non-Susy is in the Swampland, connection between Euclidean wormholes and the weak gravity conjecture, neutrino masses, the repulsive force conjecture, which is a cousin of the weak gravity conjecture. We did talk a bit about covariatisms, but we didn't talk about the relationship with bubbles of nothing. There's this and much more that one could talk about, like the convexity of the operator spectrum, also related to weak gravity in ACFT. And if you're interested about any of these topics or anything else, I'm happy to talk about anything during the gather town or any other time. The take-home message of the talk, for those of you which were not that familiar with the Swampland program, is that quantum gravity imposes non-trivial constraints at low energies that are not apparent from an effective field theory point of view, and we are just beginning to uncover. Working in the Swampland is very fun because it's very interdisciplinary. So some of the results that I presented in this talk involve hardcore string theory, holography, quantum information, algebraic geometry, topology, or even ideas coming from particle phenomenology. So it's very interdisciplinary. It enforces very strong interactions between different fields. And this is why programs like this are so awesome, because they bring together people from different fields. And that's what one of the things one primarily needs as a Swampland researcher. So I'm excited. Very excited about this program that is happening, and I'm also excited to find out which kind of things we'll figure out together this week. So with that, I thank you for your attention and hope you enjoyed the hike.
Very good, Miguel. Thank you very much for this excellent review. You covered many things. Of course, one cannot cover everything, but we have time for discussion, maybe a few more questions now or later, or also during the gather town break. Mm-hmm. But the stage is set very nicely. So is there any more question? I think the hand of Alexander is still there, or is it a new question?
Sorry, I didn't lower the hand.
Good. So for the moment, I don't see any more questions. Well, there's a new hand. Is Daniel's hand new?
Yes, my hand is new. I just had to find the hand button. So it took me a while. Yeah, I just wanted to make a small comment. You said on your last slide that 10D back reaction DGKT is not known. So in the meantime, this has actually been computed. I guess we will talk about it tomorrow.
Yes, yes.
So I just wanted to briefly mention that. So
yes, sorry,
there's some progress on that.
No, sure. The DGKT slide that I had here was very schematic because tomorrow is the day about that. Yeah, definitely.
Okay, so a great talk. Thanks.
Thank you.
All right, so if there are no more questions.